Sally Zhang is an assistant research scientist in the Department of Earth and Planetary Sciences at Johns Hopkins University. Before she joined Johns Hopkins, she was an advanced study program postdoc fellow at the National Center for Atmospheric Research. She received her PhD in environmental science and engineering from Caltech, and her research interests include polar cloud dynamics, Southern Ocean teleconnection, and tropospheric transport. So why don't you take it away, Sally?
Yeah, thank you for the opportunity to talk today about my research. So the title, I just shortened it to be the response of tropospheric transport to abrupt CO2 increase. And before I start, I'll acknowledge my collaborators, Darren Wall from Johns Hopkins, and also Clara Orbe from NASA GISS. So on the right, you can see a satellite image overlooking the UK and Western Europe. And I thought this is a really cool image to demonstrate what transport of pollutants look like in real life, as opposed to just looking at model data. And for example, north or northwest of the UK and Ireland, you can see these swirls of dust and aerosols that really show a turbulent nature of the flow. And just by comparing the size of these flow to, for example, the clouds that's further to the east, you can really see that the scale of these flow of pollutants is much larger than these cloud scale features that we see to the right. So these are really large scale flow features that can bring smoke of wildfire, in this case, from the UK, but also I think part of some spots in France that are blown over the ocean and further brought into the higher latitude regions. So the focus of this work is really motivated by looking at the short-lived climate pollutants, which are very powerful climate forcers. So on the left, we see a diagram comparing the lifetime of different pollutants, including CO2, which has lifetime of hundreds of years, to other pollutants such as the hydrofluorocarbons, methane, black carbon, ozone, all of which have much shorter lifetime comparing to CO2, ranging from hours to days in the case of ozone to more than a decade for hydrofluorocarbons. And although these pollutants are relatively short-lived comparing to CO2, they can have quite a large climate impacts. So for example, over a 20-year period, these short-lived species can have hundreds or even thousands more times this climate impacts than a unit of CO2 has. And all of these pollutants have, they all have anthropogenic sources coming from either industrial or agricultural origins. So these trace gases and aerosols have climate, health, and also ecosystem impacts. And in particular, when we think about pollutants in the Arctic, they also have climate impacts. And for example, if we look at a few of these pollutants, sulfate aerosols, for example, they can reflect sunlight quite efficiently, but they can also impact or interact with clouds, which is a key uncertainty in climate change projection. So on the right is the schematic showing in winter what sulfate aerosols can do in terms of the impacting the surface energy balance. So when we compare a cloud that is relatively have fewer aerosols than a more polluted cloud, these aerosols can increase the long wave optical depth and enhance the downward long wave emission at the surface, so that having these aerosols can actually have a positive cloud radiative effect or a radiative effect at the surface. And we can also think about black carbon, which is another pollutant, quite important for the Arctic because they are dark and they absorb sunlight, especially on relatively clean surface, such as snow. And other trace gases such as methane and ozone can have a local greenhouse effect as well. So naturally, we would like to know how will these pollutants change in a warming Arctic. And to think about the changes, I guess it will depend on how emissions of these pollutants change. But another component is also how the transport of these pollutants change, because a lot of these pollutants don't originate in the Arctic. They're brought into the Arctic by atmospheric flows. And here is a, I think, rather complicated schematic showing different processes that contribute to the transport of pollutants into the Arctic. And so the Arctic is in the middle, and you can see a interesting representation of Greenland on the left here. But so the Arctic has these dome-shaped feature here representing basically the potential temperature structure of the atmosphere. So because the Arctic is much cooler than the lower latitudes, if we think about potential temperature surfaces, the Arctic would fit into this dome. And we think in terms of the potential temperature, so the isentropes, because if you consider adiabatic flow, that flow is going to largely follow the contours of constant potential temperatures. So for example, some of these arrows are kind of following the sloping theta surfaces, so the dome shape. And there are a lot of different processes happening at different time scales. There are fast and slow time scales, but also low-level transport and descent from the higher altitude. And a lot of these features are represented in climate models because they're larger scale and the processes are resolved. So we can use climate model to study the large-scale transport and how these would respond to climate change. So as I mentioned earlier, the transport is shaped by large-scale circulation, and which allows us to use climate models to simulate the transport. And one way to approach this problem is to include passive tracers that don't interact with the atmospheric flow or the climate, but they're brought along the atmospheric circulation. And we can study how these transport responds to increasing greenhouse gases by analyzing the tracer response without changing the emission. So to simplify or to isolate the impact of emission changes from transport changes. And there is a huge amount of literature looking at how the large-scale circulation responds to CO2 forcing. And I'm just showing a few that are often discussed in the literature that we know relatively well. So on the left is a very simple schematic showing the zonal mean circulation, and the arrows on the left is trying to represent the Hadley cells. And we have the tropopause in dashed line, and then the mid-latitude jet to the right. So we know that under increasing CO2, we expect the tropopause to rise, and also the Hadley cell edge to expand poleward, and also the jet is expected to shift poleward. However, if you look at how climate models simulate climate change and how the jet responds to climate change, there is actually a large spread across models to represent the response of this jet shift. So on the right, I'm showing you the box and whisker plot showing the distribution of the CMIP5 models in their simulated jet shift for the southern hemisphere, which we only consider the zonal mean structure, and then the two basins in the northern hemisphere, the North Atlantic and North Pacific. And each circle is showing either the annual or the seasonal response. And in the southern hemisphere, it seems like in almost all seasons, the jet is going to shift forward. So it's relatively well constrained, although there's still quite a amount of spread across models. So the magnitude is still uncertain. However, in the northern hemisphere, it's even more uncertain. For example, in the northern hemisphere, North Atlantic in DJF, so the winter, the mean of the model is close to zero, and you have about half of the model simulating a polar shift and half of the model simulating equatorward shift. And similarly, in the North Pacific, you have a disagreement amongst models of whether the shift is going to be poleward or equatorward. So the northern mid-latitude jet response in DJF is probably the most uncertain, given the CMIP5's model representation of the climate change response. So on top of this uncertainty, we also discovered that global warming itself might not be linear with CO2 forcing. So this kind of study can potentially help us understand what is causing the large spread and uncertainty across models. And this is one of the examples. So on the left is a figure showing how the global mean surface temperature response changes as a function of radiative forcing, or alternatively, the amount of CO2 we increase in the climate model. So we can first look at the blue dots. So these 4 dots, you can ignore the red ones for now, are at 4 different CO2 concentrations. So we have double CO2 3 times, quadruple, and 5 times, CO2. And the global warming that you get from 2 to 3 seems to be different or shallower than the slope that you get from 3 to 5. So there's a change of slope of the global warming as a function of CO2 concentration. And this nonlinear behavior seems to only present when we have a dynamical ocean. So when you switch to a slab ocean, so you remove the ocean dynamics, which is shown in the cyan, this global warming as a function of radiative forcing becomes linear. And there are also other metrics in the dynamical sense that, for example, the helical edge or strength, that even show a non-monotonic behavior as a function of radiative forcing. So they can increase at first and then decrease when you go to higher CO2 concentrations. So that's a very curious feature that we've seen in multiple climate models at this point. So the question that I would like to address with my research is how and why will tropospheric transport respond to increasing CO2? And in particular, can we use the circulation changes that we have known about to explain these transport response? So a quick outline, I'll keep introducing the method and the model that I'm going to show. And then we'll talk about, I'll show you the response to abrupt CO2 increase for the climate and also for the tracers. So to answer this question, I'm using model outputs from your in-house model, the GISS E2.2-G model. This is the high top version of the GISS CMIP6 contribution, and it's a fully coupled model that we force with pre-industrial and also abrupt CO2 forcing scenarios. So in particular, I'm looking at the 2 times and quadruple 4 times abrupt simulations. So all these simulations are run to quasi-equilibrium for about 150 years. And the reason that I'm using or looking at this model is really the fact that it has included some idealized passive tracers that are very valuable to examine changes in transport. So at first, I will look at the non-interactive configuration. So in this configuration, there's no interactive chemistry. And just to distinguish this from maybe some of the other named historical simulations that perhaps you're more familiar with, in these simulations, the ones that I'm looking at, there's no representation other than water vapor's response to CO2 forcing in these runs. So because these are abrupt forcing runs, even when I double or quadruple CO2, there's no change in any other tracer concentrations. So it's only the water vapor that's responding to this and interact with the climate. And as I mentioned, there are idealized tracers included in these runs. And here's a table showing all the amazing tracers that are present in these simulations. And in particular, I'm looking at the NH5 or 50-day loss tracers that are there to evaluate the mid-latitude Arctic transport. So I will definitely go into details of these tracers, but before that, I just want to say that these tracers were first included in the Chemistry Climate Model Initiative to study the transport of pollutants from the mid-latitude to the Arctic and what is driving the differences across models. So on the left is a spaghetti diagram showing the concentration of this tracer at the mid tropospheric level as a function of latitude. So each color is representing one model, and you can see a very large spread in the climatological distribution of this tracer. And having the identical tracer implemented across different models enables us to understand what the cause of the spread is. And in this case, people have found that the large intermodal spread in the distribution of this very simple passive idealized tracer is due to the differences in parameterized convection, especially over the ocean. So what does this tracer actually look like in the model? So I'm going to focus on NH50, which stands for Northern Hemisphere tracer with a 50-day loss time. So this tracer has a source at the surface which has fixed mixing ratio from 30 to 50 north. So it's shown by the 2 dashed lines, the 30 and 50th degree boundaries. And then this is the near surface concentration of this tracer in the climatology in the winter, Northern Hemisphere winter. And you see that the highest concentration of NH50 is found within the source region, which is completely reasonable because that's where the tracer concentration is fixed. But then outside of the tracer region, the source region, you have a decrease of concentration as you move poleward or equatorward. And in general, the concentration north of the source region is higher than south of the source region. That itself is already interesting, telling you something about the general transport of a tracer of mid-latitude origin. So if you move higher up into the troposphere, this NH50 concentration looks very different. So overall, the concentration is lower than near the surface, which makes sense. But then the concentration is really much higher when you're further north into the high latitudes. At some longitudes, it looks even quite monotonic, so it just keeps increasing towards the pole, the North Pole. Whereas in other regions, so there is some zonal asymmetry in this tracer. And we can also look at the zonal mean of this NH50 tracer, and it looks like to the right where x-axis now is latitude and y-axis is pressure. So the darker the color, the higher concentration is. And it is the highest near the surface, where this black bar is representing the source region. And then it gradually decreases as you move higher up into the troposphere. But it definitely has this distinctive shape that tilts towards the mid-troposphere in the polar region. So we can already overlay these surfaces of constant potential temperatures, so the isentropes that I mentioned in the beginning. So these are contours where you would expect adiabatic flow to follow. And the contours actually align quite well in some circumstances with the climatology of this NH50 tracer, which is suggesting that the tracer distribution itself is happening or it's shaped by isentropic flow. So I have introduced you the tracer that I'm going to look at, and next I'm going to show you the response, first the climate response to abrupt CO2 forcing in the GISS 2.2-G model. So I'll start by showing you the surface warming pattern. And this is, I guess, a first clue into why there is a nonlinear response that at least I didn't expect before I start analyzing these runs. So it's showing you the DJF surface air temperature response, and on the left, so a lot of my figures are going to have three columns, and they're usually ordered by the 2 times response, the 4 times response, and then the nonlinearity. So I'll define what this is, but basically to quantify the difference between the 2 and 4 times. So on the left is the response, the non-interactive configurations response to CO2 doubling, and it's truly a global warming pattern, with the exception of the Southern Ocean, where we see very little warming, which I think in itself is very interesting. But the warming is heavily amplified over the Arctic region. That's where the strongest warming is found. And then when you look at the quadruple response in the non-interactive configuration, it's not merely a doubling of the response to the left. You actually have features that were not there in the 2 times, namely this North Atlantic warming hole. So in this region, we actually have a cooling, an absolute cooling after you quadruple CO2, which is very interesting. And despite having this, you still see very strong Arctic amplification. So to compare whether the any quantity is respond linearly with CO2, I can normalize the response of the quadruple case and then subtract the response of the CO2 doubling. So this is how I quantify nonlinearity. And if we talk about surface temperature, so in this case, if we look at the global mean surface temperature response, so I'm putting the numbers here. So for the doubling, we get about 2.1 Kelvin. And then for quadrupling, we have 3.7 Kelvin warming. So for the nonlinearity, we get a negative 0.25 degree. So that's basically the mean over panel C. So we get about 1/4 degree cooling that shows up as the nonlinearity. And this cooling, again, is highlighting the presence of this North Atlantic warming pole, but it definitely goes beyond the North Atlantic. You can also see quite a bit of cooling over the Pacific high latitude region as well. So this is the surface climate. And next, we're going to look at the vertical distribution of temperature response. So again, 3 panels showing you the response of 2 times, 4 times, and then the nonlinearity to the right. So for temperature in DJF, for 2 times, this is the typical global warming pattern, zonal mean pattern that we've seen across very different climate models. So we have this amplified warming in the tropical upper troposphere, and then the polar, the Arctic amplified warming that is the strongest near the surface. And then for 4 times, it looks like just an enhanced version of the 2 times. But if we calculate the nonlinearity explicitly, this surface amplified cooling shows up, which corresponds to the map that I showed you on the previous slide, that there's quite a strong cooling over the northern high latitudes. And this cooling definitely extends further into the troposphere, and it will enhance the meridional temperature gradient almost throughout the troposphere. So the changes of zonal mean temperature, meridional temperature gradients can have an impact on the mid-latitude jet or the zonal wind, which is shown at the bottom. So at the left, we have the zonal wind response for the CO2 doubling case, and we see very weak response in the northern hemisphere, but in the southern hemisphere, we have a poleward shift, which is what we expect based on other climate models. And when we move to the 4 times, now the northern hemisphere is showing a significant response. And yeah, I forgot to say that the contours are always showing the climatology, so we can see where the response is relative to the climatological mean. So here, in the 4 times, we can definitely see a polar shift of the zonal wind maximum. And if we, again, calculate the nonlinearity to the right, it shows up as a strengthening and also a poleward shift of the mid-latitude jet. So this is the climate response that I'm going to highlight. And next, I'm going to show you the response of NH50, the tracer that I'm focusing on. So NH50 response turns out also to be nonlinear to CO2 forcing. And again, on the left is from the CO2 doubling case. The main response we're seeing is this decrease over from 30° north all the way to the polar region in the lower troposphere. There's a decrease of tracer concentration. And then above that, in the upper troposphere, we have a positive tracer anomaly. And when we move to the quadruple case, again, it's not just an intensification of the response that we see in 2 times. It actually has quite a different pattern of the tracer response. In particular, we have a very strong decrease of tracer concentration right above the source region in the mid-latitude that extends for the majority of the troposphere. And this negative anomaly also extends into the Arctic lower troposphere and into the upper troposphere in the tropics. And above that region, we have, again, this red, so positive anomaly of tracer near the tropopause. So if we try to quantify the nonlinearity of NH50, it's shown on the right, and it's really showing this dipole structure where we have a decrease of tracer in the upper troposphere in the mid-latitudes, or extending from about 800 hectopascal all the way to the tropopause, and then a positive anomaly poleward of that. So an increase of tracer in the lower troposphere in the high latitudes. So we can really tie the response of the jet, so this poleward shift of the jet, to the response of the tracer. And because the tracer is passive, we know that only the circulation can change the tracer, but not the other way around. So in terms of the nonlinearity, we have already seen that there's a poleward shift of the jet, which is also showing a strengthening on the poleward flank. And that is going to correspond to an increase of the eddy kinetic energy. Thus, it's representing an enhanced mixing that happens mostly along surfaces of constant potential temperature. So increased eddy isentropic mixing. And this is going to shape this dipole structure of the NH50 tracer. And how this works is that I'm overplotting the surfaces of constant potential temperatures. So let's select one, let's say the 300 Kelvin contour. And given that we know at this latitude, we have increased eddy kinetic energy, so it's going to increase mixing that's along this 300 surface. So this contour is connecting the upper troposphere to the tropical lower troposphere. So we know that in the tropics, the tracer concentration is much lower than further poleward. So when we increase mixing here, we're actually increasing the mixing with low tracer concentration air into the upper troposphere in the mid-latitudes. And to compare this to, let's say, the 280 contour, so the 280 surface, which intersects the source region of this tracer. So when we increase, again, mixing in this region, it's going to bring air with high tracer concentration into the upper troposphere in the high latitudes. So therefore, enhanced eddy mixing that is throughout the mid-latitude tropospheric column is going to create this dipole structure because of the way that the tracer is distributed and also how the isentropes are shaped in the climatology. And another way of showing this relationship is really to look at the correlation between the zonal wind and NH50. And on the left, I'm showing you the time series for both 2 times and 4 times CO2 experiments. And the solid line is showing the NH50 concentration averaged over the mid-latitude in the northern hemisphere in the entire troposphere. And the y-axis on the right is representing NH50 concentration, and I've flipped the values so it's going downward as you increase the NH50 concentration. And then the dashed line is showing the zonal wind, again, average over the column at mid latitudes. And these two curves for both cases really go hand in hand, and they're almost perfectly correlated as shown on the right. So it's another way of showing the left figure, but now doing a scatter plot. And their correlation coefficients are also shown here. In both simulations, they're very high. And it's also high even when you remove the linear trend that you can see, for example, in the 4 times. There is generally a increasing trend for the zonal wind. So every time when you have high wind speed over the mid-latitudes, you tend to decrease the tracer concentration. So that is showing this blue blob in the dipole structure in the mid-latitudes. And this is really showing a robust relationship where the zonal wind variability is causing tracer to change its concentration from year to year, but also from decade to decade. So just to summarize the response in the non-interactive runs, we have in the 2 times CO2 case, really strongly amplified warming in the Arctic, whereas in the 4 times, the North Atlantic shows quite a robust cooling. And in the 2x case, we have a slightly weakened northern hemisphere jet, whereas in the 4x, the northern hemisphere jet shifts poleward. And the differences between the jet response definitely impacts the transport, whereas in the 2x, we have just in general weaker transport in the mid-latitudes, whereas the 4x we have increased eddy mixing and transport into the Arctic to result in that dipole structure of the tracer. So that was the nonlinearity in the non-interactive runs. And next, I'm going to demonstrate that this relationship between the jet and the tracer is really robust across different scenarios and different configurations. So I'm going to bring in another set of simulations. These are the one moment aerosol configuration of the E2.2-G model, where the aerosols and trace gases are calculated interactively. So it is definitely a more complex version of the model. And we want to see how in this version, the transport response can differ from the non-interactive. It's the same forcing scenario and also the same simulation length. So first, I will again show the surface air temperature response. And what is quite obvious here is that in the OMA runs, both the 2 and 4x simulations have the North Atlantic warming hole. So the both OMA and 2 and 4x runs look more similar to the 4x non-interactive run compared to the 2x non-interactive, where the warming hole is absent. And I've also labeled the global mean surface temperature response. So in the OMA, the global mean warming is weaker than in the non-interactive in both cases because of the presence of this North Atlantic cooling. And if we calculate the non-linearity in the OMA run, it's actually showing up as a slight warming over the North Atlantic, which is saying that the cooling over the North Atlantic in the 4x OMA is not as strong as what you expect if it's linear in the OMA 2x. But this nonlinearity is weaker than the nonlinearity of the opposite sign in the non-interactive run. And these will definitely have an impact on the atmospheric circulation response, which I'm going to show next. So here are only the OMA 2 and 4x response along with the nonlinearity to the right. And the top panel is showing again the zonal mean temperature in the 2 and 4x OMA runs. And these tropical warming in the upper troposphere is still present and robust in these two simulations, but there's a huge difference in the high latitudes in these two runs, whereas in the 2x there is an absolute cooling in the zonal mean, which is really interesting. I think it's not normal to see this absolute cooling showing up in the zonal mean temperature response in climate model simulations. And then in the 4x, it's, although not an absolute cooling, it's definitely not as much Arctic amplification as what you would expect based on what we saw earlier in the non-interactive runs. And this pattern is quite consistent from the 2 and 4x, saying that the nonlinearity in the OMA run is weaker than in the non-interactive. And again, these strengthened meridional temperature gradients in both simulations can produce enhanced baroclinicity and also a poleward shift of the mid-latitude jet, which again is present in both simulations. And there's very little nonlinearity in the zonal wind response. And here the black contours are showing the eddy kinetic energy response. So again, in regions where we have a positive zonal wind anomaly, we also have a positive EKE anomaly that is in line with where the wind strengthens. So given this response, I would also expect the NH50, so the tracer, to look quite similar in the OMA 2 and 4 times. So there's less nonlinearity there. And that is indeed the case. So this slide is showing the response of NH50, comparing them for the non-interactive that we saw earlier and the OMA at the bottom. So before, I've highlighted the difference or the nonlinearity in the non-interactive run. And when we do the same for OMA, the nonlinearity is much weaker. But even looking at the individual simulations response of NH50, it looks quite similar to the non-interactive 4 times. And it has this pattern of negative tracer anomaly in the mid-latitudes and a positive anomaly in the high latitude upper troposphere. So these the tracer response corresponds to the zonal wind response really well in the mid latitudes where we have a polar shift of the jet. Another way to compare cross simulations is to really look into the difference between the non-interactive and the OMA configuration of the model. And given that the 2 times has the largest difference, I'm going to focus on the comparison of these 2 simulations. So just to, again, review what we saw earlier of the surface air temperature response, in the non-interactive 2 times, it's global warming, at least in the northern hemisphere, whereas the OMA 2 times response has this significant cooling over the North Atlantic. And when we calculate the difference between these 2 simulations, we are getting this cooling that extends from the northern mid-latitude all the way into the Arctic. And this is, again, going to reproduce a mean temperature response that strengthens the meridional temperature gradient throughout the troposphere that gives rise of a polar shift of the mid-latitude jet, which is represented in the middle here. So this is the zonal wind difference between the OMA and non-interactive 2 times CO2 response. Again, this poleward shift of the jet is producing this dipole structure of the NH50 tracer. Again, the changes or the contours of the tracer response really align with the contours of constant potential temperatures, which is suggesting that a lot of the changes in the tracer is happening along the isentropes. So we have a decrease in the mid latitudes and an increase in the high latitudes. So to summarize this jet tracer relationship in the winter, I have this schematic on the left. It's again representing the zonal mean structure of anomalies of all these different fields that I'll go through. So the bottom boundary is showing where this tracer is originated, so between 30 to 50 north. And we have these gray contours showing surfaces of constant potential temperature. So in terms of circulation, whenever we get a poleward shift of the mid-latitude jet, that is represented by the black contours. So it's a positive anomaly of the zonal wind, which is happening slightly poleward of the climatological wind. So these positive zonal wind anomaly gives us enhanced eddy mixing, which is shown by these wavy arrows that happens mostly along isentropes. So the gray contours are showing the isentropes. So we have these 2 arrows showing anonymous increased mixing. And for the tracers, we have first this increased mixing that is with high concentration air from the mid latitudes, therefore giving us a positive tracer anomaly that's poleward of the source region. And then above the source region, higher up in the troposphere, we have increased mixing of low air of low tracer concentration. Therefore, we get this blue, which is a negative anomaly of the tracer. So the dipole response of NH50 can be explained by the changes of the zonal mean jet. So all I've shown so far is looking at this one tracer that has a 50-day loss rate originated from 30 to 50 north with no zonal asymmetry in the source. We have also found that this pattern is robust across different tracers. And at the bottom, we have NH5, which is a similar tracer to NH50, but has a shorter lifetime. So it gets removed faster than NH5. And again, this dipole structure is still present. We have a decrease above the source region and an increase poleward of the source. And we also have two more realistic versions of tracers, so SO2 and black carbon to the right. Both have much or very different source and climatological distributions that's showing contours. But the response to CO2 doubling actually looks quite similar to what we saw above in the schematic. Again, it's this decrease of tracer above the mid-latitude source region, and then a increase of tracer concentration poleward of that. SO2 and black carbon have very different chemical processes and also different lifetimes, yet their first water pattern in their response to CO2 looks quite different. So that's encouraging that the mechanism we are discussing here can be used to also explain more realistic tracers. So the last bit of time, I just want to hypothesize why we see such different responses in these four different simulate configurations of the same model. And obviously, having the interactive chemistry seems to make a big difference in the North Atlantic. And this cooling will naturally make me think about the response of AMOC, and that is shown to the right. So it's two lines showing the non-interactive time series of AMOC. The orange is the 2 times corresponds to panel A, and then the green is corresponding to panel B. So the green, the 4 times, has a weaker AMOC at the end of the simulation than orange, where the AMOC basically has no change compared to the pre-industrial shown by the gray bar. And the two OMA runs both have stronger AMOC decline than their non-interactive counterparts. So the dashed orange is showing actually a similar trajectory of AMOC to the non-interactive 4 times, whereas the OMA 4 times response has a basically collapsed AMOC. So although here we're not really showing the causality between the temperature response and the AMOC, studies have suggested that models with stronger AMOC decline tends to have a more poleward mid-latitude jet, which is a composite study here looking at both CMIP5 and CMIP6 models. And again, that's not really telling us causality because it's just a correlation here. But there are studies where they can actively change AMOC and look at the response. And in this study in particular, they artificially reduce the strength of AMOC by hosing the North Atlantic. And when you look at the surface temperature difference, it looks quite similar to our non-interactive nonlinearity pattern. And this also turns into a strengthened meridional temperature gradient and a poleward shift of the jet. So this experiment supports the idea that the AMOC weakening can drive a difference in the modeled mid-latitude jet response. So to summarize, we explored the transport response of a tracer of mid-latitude origin in 2 configurations of the GISS E2.2-G to abrupt 2 and 4 times CO2 forcing. And the changes in the isentropic eddy mixing associated with the mid-latitude jet dominate the response of the tropospheric transport. And the process is, again, highlighted here in the schematic. And we think that the differences across the simulations is caused by the differences of the AMOC response, although we still have to work on establishing this causal relationship between the ocean dynamics and the atmospheric response. And some implications, so there is substantial change in the transport with increasing CO2 even without changing emissions. And the response of the transport seems to be sensitive to the response of AMOC. And it's also highlighting the difference between non-interactive and OMA is that the AMOC seems to be sensitive to atmospheric chemistry, which is really interesting by itself, that suggesting stratospheric ozone's response to CO2 can drive differences in the AMOC. And also the last point, the nonlinearity is much weaker when we have interactive atmospheric chemistry. So is that suggesting that the real world is almost always more linear than what models of less complexity suggest? I think that's a question that I'm always interested to explore more. So that's it. Thank you for your attention, and I'd be happy to take questions.
Thank you so much, Sally. We already have some questions in the room.
Yep.
Hi, Sally. Thank you for that very wonderful, clear talk. I know you focused on Northern Hemisphere winter, which is the more dynamic season. I wonder if you thought at all about what would happen in summer. Two things come to mind. One is the temperature difference between the equator and pole is much less, so the isentropes will be flatter, which might suggest that everything would get moved down. But in addition, the jet is normally at a good deal higher latitude to begin with in that season. And I wonder, with respect to the tracer between 30 and 50 north, whether it may be too far north for changes in the jet to have as strong an impact on the tracer.
Yeah, thank you for your question. And it's definitely something that we have looked at. And we decided to focus on DJF because I think that's where this nonlinearity really shows up. And it's quite interesting to explore. In the summer, actually, the tracer response is quite linear. And as you mentioned, the mixing process in the summer can be different from the winter, whereas you don't have the same dominance of this eddy mixing happening in the summer. Perhaps more convective processes dominate in the summer. And there, the tracer response, even with the presence of the North Atlantic difference, is actually quite linear between the 2 and 4 times. So yeah, that's definitely a very different mechanism in that season.
Thank you.
Thank you.
We don't have any questions in the chat right now. So if anyone online, if you want to unmute and ask a question, or if there are any other questions here. No? Okay, then can we just give another round of applause for Sally? Thank you so much.
Thank you.
And yeah, I think we can sign off. And thank you, everyone, for coming.
Thanks. Have a nice day.
Thank you so much, Sally.
Thank you, Sally.
Good day.
Thank you.